The first speaker is Özgür Müstecaplıoğlu. And you may need no introduction for most of you because he's really well known. But for those of you who doesn't know him, he did his PhD in Weekend with Shumowski and then had his postdoc in Georgia Tech. And then after that, he's been to Koç University ever since and been in and out during some research visits. And of course, recently he's got interested in this new niche called quantum thermodynamics, and he will be talking about that today. And the title of the talk is Quantum Thermodynamics and Limits of Quantum Machines. So please welcome.
Well, thank you very much, Nanch, for this nice introduction and also putting some pressure on me. This is my before lunch talk. Yes. All right. And thank you for our organizers for this wonderful event and bringing us all together here. So also I'm very happy for the order of the talks today because I want to make a small connection with the excellent, fantastic talk by Professor Özgür. So basically, Ceyhun asked a very nice question that if this could be mass and the negative temperature can be related to each other. So if you can imagine a density matrix of several atoms, yes, let's take even two atoms with excited ground excited and ground level. So basically these are two spins, yes. So then we can have these energy levels and we can map them to basically decay basis, yes. So then if you put this in an energy basis, you have a 4x4 density matrix, yes. So after, whenever you populate any elements here, you are actually putting some negative temperatures, okay? But if you are away from the main diagonal, you have coherences. That is what Professor Özgür said, that these states are beyond more than negative temperatures and we have superpositions. And when you have coherences also populated in addition to negative temperatures, you can break the standard quantum limit, yes? Now I would like to ask what happens here, okay? So this is my talk. All right, so of course, I cannot thank enough to many people who helped me in this adventure in thermodynamics. It's, there are many different thermodynamic laws, as many as people thinking about it. So I got many different views on what we are doing. So I thank all of them for positive and negative feedback also. Of course, I have to make some disclaimers, starting with some giants like Sommerfeld. He said that basically, if you think about thermodynamics once you understand, you think you understand it, but if you think more and more, it becomes not understanding, but it becomes somewhat like dogma. Yeah? It becomes a habit. So thinking out of this is a little bit challenging. And now what I want to do is I want to put some quantum thermodynamics. I want to put some quantum salt on this. So sorry about that. So after my talk, if you don't feel safe or good, so I just have a disclaimer here, okay? All right. So my motivation is we are all excited about fundamental and practical promises of quantum technologies in this new quantum world. But like many progress of mankind, I want to ask what are our limits, or why should we have any limits? Why too? Yes. So okay. So basically, let's look at in the past. Are we limited in the past so that we are still trying to push? We were not happy. Well, we were not happy because of actually one little problem. I would like to mention that in the first industrial revolution, we had all these nice steam engines. People were doing textiles, important for our country as well. And we managed to make it more efficient, still harnessing the power of the heat. But somebody said that don't get so excited, I can limit your efficiency, okay? Thanks to Mr. Carnot, I cannot do it perfectly, okay? Well, then we think this is not stopping us, we think forward, then we do one more revolution, yes? Then we discovered electricity, we started to harness the energy of electricity, electric energy. Then we make more efficient motors and engines. Then we can make more and more rapid production, mass production of the things. Still, these are using heat, but basically you can use electric engine here, make mass production. But again, both the electric engine and these guys, Carnot will tell you that you don't get so excited. Okay? So this is the second time we encountered this Carnot limit. Then again, we are not going to stop. We will go forward. Let's escape from the heat completely. Let's make a laser. Let's make computers and so on. Okay, or go nuclear. Well, whatever we do, it seems that we are bounded with some Carnot limit. Okay. All right. So in all of them, we cannot escape this. But yeah, what is this Carnot limit? Maybe for students, I can remember it. Basically, it started with a very local motivation. Yes, very maybe national motivation. Let's make the best engine for our country. And how can we do it? Well, basically, an engine harnesses some energy from a source, like a heat, steam, then make it run through some engine and emit some heat into some sink-like environment. Then you make some useful work out of all this business, and you want to do it most efficiently. Okay, how you can do this? You define efficiency, a figure of merit. This is basically cost and gain out of this process, your work and input heat. And then if you do this business, you realize that you have to somehow manage to transfer heat through your engine very efficiently. How can you do this? You want to do it in a non-reciprocal, you want to do it in a reciprocal manner, in a frictionless manner. Okay? Irreversibility and reversibility issue enters here. So what you do, or what Carnot suggested, let me consider some isochoric heating and cooling stages, normally in standard engines, and let me replace this isochoric, that is keeping the volume constant, and relax it a little bit. Let me give my engine a little bit freedom so I can expand and shrink during the heating transfer. Okay? So by this way, you can make sure the entropy will not be bothering you, and you make these irreversible changes. These other stages of expansion and compression can be the same, but if you change this isochoric heating stage and make it also frictionless, then you can have a very efficient engine, giving you some kind of value that only depends on the properties of the sink and the source, independent of the details of the engine. This is known as Carnot bound. Okay? Well, as long as you have these temperatures, hot and cold temperatures, you have a fixed bound. Okay? But we have developed, of course, many non-thermal devices, so why should we worrying about this? Yes? So let's look at that. So of course, maybe ancient people have a right to worry about this because they all have hot bed and cold bed, the atmosphere, to cool down their engines. But if you are having lasers, why should you worry about this? Okay, so really we can beat Carnot maybe if you use non-thermal devices. Well, in 50s, people excited about this progress of Charles Thornes explained that I have a specific modern device called maser, okay, which harnesses the electromagnetic energy. But other people, a couple of years later, Scoville and Du Bois, they come with an idea that actually this operation can be mapped to a Carnot engine. Okay? So it will be a very efficient device, but it is still bounded by a Carnot engine. Well, even the most interesting non-thermal looking device seems to be suffering from this Carnot engine. Okay? So my approach, my method to investigate also modern quantum machines will be to follow what Scoville and Du Bois did for the maser. Okay? I want to look at these new inventions from the eyes of a thermodynamical physicist, that can I map these devices to some thermal engines effectively, not necessarily with genuine temperatures. Okay, so basically, our resource nowadays is the Schrödinger wave function, okay, quantum resources. Then can I boil my Turkish tea with this, and or just can I pull some stuff? Yeah. Well, but of course I want to actually, you know, every physicist is like a little kid. My kids wants to understand something, they just take this and crash and try to see what's this, yes? So also we try to break here a standard quantum limit like a little kid. Then I want to break here also something. I want to break the Carnot bound. Okay, so my motivation is not that little bit naughty, not that nice. Okay. All right, so what is my advantage here? So far, we couldn't beat Carnot up to here, but I have a great hope with quantum. Why I have great hope with quantum? Because we know that maybe quantum machines with this quantumness can help us, and maybe we can remove our frustration that not maybe infinite power, but maybe with at least breaking the second law of Carnot, because we have very optimistic. Yes, why we don't like thermodynamics with our students, but more with quantum mechanics, because it gives us some sense, maybe false feeling of freedom. Yeah. Well, there is a problem and catch that we hope that thermodynamics should get less and less valid if you go to smaller and smaller dimensions. Of course, thermodynamics is not maybe that small. At least for companies, you need to scale up your number of qubits for large numbers. But in principle, we want to reduce the dimensions and deal with finite systems and hope that maybe thermodynamic bounds can be broken. Well, the term quantum thermodynamics is not very maybe meaningful at first sight, because we don't expect thermodynamics valid in small systems. It is already designed for macroscopic systems. But this is actually the problem. Yes, why then it still tells that my maser cannot work efficiently? Yes? Well, so we hope that maybe using the quantum mechanics, this second law of second law, at least one of them, there are many second laws, but at least one of them, Carnot bound, can be broken. But of course, this is also written on stone. That means maybe I will introduce new bounds when I break something. Okay. Well, I am not alone. There is a quantum cowboy, Marlan Scully, who also thought about this. He likes to maybe drop some stones from time to time and create a lot of confusion and new problems. So in one of his that kind of studies, he examined a kind of engine, which is Otto engine, very similar to our standard car engines. And he found that if he uses quantum working principles and quantum extension of the Otto cycle, he could really get a more efficient result. But this is not Carnot bound, so this is not fundamental bound, but it will be improving the efficiency of a classical engine. So it gives us some hope. It gives us some hope that can I do the same with the Carnot cycle? Well, I didn't think about this. Scully kept thinking about this, but he realized that he needs some help. Okay? Well, he needs some otherworldly help, actually. So they just plotted a pentagram, and Professor Scully conjured some friends with their holy books. Yes? So Grisha Garwal, we all read these books in our quantum optics courses or other courses. Then they also get help from late Professor Walter, who is, of course, one of the fathers of quantum optics experimentally, macromaser and other beautiful experiments. And one more, of course, Professor Zubari also there. So these four giants, four stars of the quantum optics and statistical physics, they come and they together get some help, hoping from out of worlds. But what they expected was a little bit different. It shows up as a name of quantum coherence. Okay? Well, they would expect maybe somebody else. Yeah? Well, this somebody else is Maxwell demon. Right? So what I want to argue that actually these quantum coherences here can play the role of Maxwell demon that can break these laws. I don't know if it is also true for standard quantum limit, but at least for my regime, it will be useful. Okay, so how it works? So how the quantum coherence can be imagined like a Maxwell demon? Well, let's take a three-level system, okay? And the lower levels, they are in some superposition state, okay? So we don't know in which one of them in this electron is. Then I can write it without forget about normalization, this state in this form, okay? Then let me send some light onto this atom. Then it's going to absorb it and get excited. But after absorption, now the electron has two options to go down. Okay, it can follow either trajectories, either to G1 or G2. Then this state in this form. Okay? So if you choose the initial superposition angle of the lower levels at a certain value, like pi, then actually you can kill the absorption. So electron will not have enough time or any chance to think about where to go. It will, it will not just get down. So you can actually kill the absorption. But if you start with excited levels, like population inverted levels, then it can just emit. So what this quantum coherence actually, that I didn't did, but what quantum coherence did is it sorted out initially excited molecules from the lower level molecules. Okay? If there is quantum coherence, lower molecules will not make energy exchange with electromagnetic bath. But if you start with excited levels, you can contribute more photons, more energy to the bath. Okay? So you can heat but not cool. Well, this is a good idea. I have a sorting machine using quantum coherence. That is exactly what this little guy will do. Okay, so let's put this here. Okay, so this will be my bath, but it's a little bit strange bath. It will start with only single atom. Okay, so it's not like a cloud of atoms. There will be only single atom there. Okay, and each single atom will be a 3-level atom. Okay, so let's put a single atom in our bath. Then let's roll it once. There is no quantum coherence. Okay, let it be in some thermal state. Okay, then what happens? Of course, the machine will work between the environment and the high temperatures at a certain efficiency known as Carnot efficiency. Okay. Well, let me introduce now my quantum coherence in the lower levels. Okay, this is actually putting a little demon and make it right and go into the cavity riding this atom. Okay. Then with the injected atoms, this atom will start and make a run and go through the cavity, and the cavity will get some heat with some efficiency, but this time more than that, or maybe less than that. It depends. It depends on this superposition. Remember that there was e to the I theta there, yeah? This theta is now phi. Sorry, forget about my notation, but theta and phi, it's just a superposition angle. So if you choose pi is pi here, then you get a plus number. So you increase the Carnot bound. Okay? We break it in a sense. But this even looks more strange. I can make the bath exactly the same with the environment. Yeah? I don't have to heat a filament or eject some atoms from a vapor, etc. I can just use the environment and take these two equal to each other and make the normal classical engine do not work at all. Efficiency will be 0. Yeah? So this will be 0, but still this is non-zero. Yeah? So that is why they called their paper that this is harvesting energy from a single heat bath. Okay? Some of the old thermodynamic people, like Kelvin, maybe, just roll in his grave after hearing this, but yeah, they call it this is a harvesting work from a single heat bath. Yeah? Well, there is a significance of that. They also suggested there are applications of this in quantum photovoltaics, but let me go through this. So what we did break really. This is we seem to be breaking the Carnot bound, but also we break the Kelvin statement of the second law. So we break two things with one stone, and even Leonardo da Vinci will tell us we are doing something wrong. Yeah? Well, we cannot publish this in French Academy journals maybe, but this is published in Science. I don't know. So, actually we can actually say that we are not breaking anything. Yeah? Because we have a non-thermal object, an information state, letting go through the micromaser cavity, and we are saying that we are doing this in a single environment, but who cares? What is important is this cavity is just a thermometer. It doesn't care what is around it as long as it can measure a temperature. And I don't have to write second law for the environments. I have to look at what is measured operationally by the cavity. And the cavity sees just the temperature still. This is what is interesting. The cavity doesn't know I am sending it a quantum information state. It only thinks that it interacts with something, giving it some energy, which is energy can be in the form of still heat, even if it's an information state. So we can define a coherence-dependent temperature, some effective apparent temperature for the information state, but a genuine temperature for the quantum thermometer or micromaser photon gas. And in this case, I can write the efficiency exactly in the form of Carnot bound, by saying that quantum information state must have an effective temperature. Okay, so we are changing the rules a bit. I mean, you can play this in iPad or some phone with some rules. It is a sorting machine, yeah. But now these are not only hot and red, yeah. So I'm going to maybe, if I knew it, I will write a new computer application and sell it in iPad. But this will be now information molecules. I'm going to sort information molecules for their temperatures. Okay. Well, you can also play another applet in Carl Wyman's contribution to thermalization, and it's a basic model or understanding of thermalization. We are enjoying it right now. Whether it is cold or bad for you, I don't know, but many molecules colliding with us. This is how we equilibrate with them. Okay. So the collision model is an important route to thermalization, to reach thermal equilibrium. But what if these molecules wouldn't be thermal, but just information carrying objects? Can you still thermalize with them? Well, what we have seen, we can actually do it, at least thanks to Professor Scully and co-workers' works. We can do it for that superposition of the lower levels in a 3-level atom. We can thermalize a macromaser cavity, a genuine thermalization independent of initial state, and so on. So how it works? This quantum coherence basically changes the collision rate of these atoms with the thermometer. So if you put coherence on them, they will collide at different rates. Some of them will collide more, some of them will collide less. So there will be some sorting thanks to quantum coherence. Okay? So this is exactly the same idea of the original idea of Maxwell, who introduced the Maxwell demon. He never used the term demon, by the way. He just imagined some concentrating, tiny-fingered, nice person. Lord Kelvin gave the name demon. But anyway. All right. So this is our thermometer now. And we can assume the rate of collision only like one atom in a thermometer or cavity at a time. And these are random events. Okay? Well, once you assume there is only one atom in it, it is easy to formulate the model and do some calculations. Okay, so let's start with a thermal atom. More atoms in more population in the ground state and less population in the upper state. Okay? Yakira Haranov actually discussed that you don't need an ensemble of atoms to define density matrix, and ensembles are not necessary for statistical quantum calculations because of non-demolishing measurements, adiabatically slow changes. We can reconstruct the density matrix using a single quantum object. So this temperature can be defined for a single quantum object. So let me also make another interpretation here. Let me break down these populations of the ground and excited states and assume these are solid marble particles and put them in a chamber where they will interact with either a cavity or quantum object, which will be my probing thermometer state. Okay? So there will be one interaction at a time and random interactions. Then I can derive a master equation for that or some simulations using quantum optic books. It's easy to find that this is the master equation. Excited state population and ground state and excited state coherence evolves through these below equations. Well, what is important to realize here, this is an interesting system. If you just dump the excited and ground states and treat them as a gas here, what are their temperatures? Excited state at -0 temperature, ground state at 0 temperature. Okay? So this gives you a whole range of, almost all range of temperatures to create in a thermometer. So if you solve the problem, defining an effective temperature for your atom, you will find that in the steady state, you can recover the usual Gibbs-like behaviors, distributions, and temperature can be controlled by the populations of the excited states and the ground states. Okay? Well, this looks like a computer to me. Yeah? Basically, a Turing machine can be considered like a collision of a processor with information molecules, information-carrying objects. Okay? So my computer has a processor or CPU, which is a head or reader of the device, and some tape which contains the information molecules. Okay? So imagine this will be just atoms or molecules in the atmosphere colliding with me, that's me, and I'm a thermometer, then I will thermalize eventually. Okay? The question is, if I can still use information molecules, can I thermalize? According to this analysis, actually this is only possible for certain information molecules, which is surprisingly not here, but here. Okay? So let's skip this. Basically, it's the energy difference, and you can introduce this energy difference through the changes of the system or thermometer state. And if the thermometer state remains a Gibbsian, this is called the Gibbs preserving map, then you can assign a temperature and identify the energy difference as if an effective heat. Okay? If it is not, if it induces some coherences on me, on thermometer, then it is a work-like state, or information state behaves like a work-like. So you can pull things instead of boiling the tea kettle with it. Okay? So I want to make a more general analysis to discuss which quantum states will be heat-like and which one of them will be work-like. So if you just start with the Schrödinger cat states and follow through this master equation formalisms, you will realize that the thermometer state after collision or tape or computer Turing-like thermalization system, by repeated interactions with the thermometer, you will find that this will induce certain coherence on the thermometer, so it can only work like a work-like coherence. So it's not a thermal information state. If you go to two atoms and like this, okay, and create some coherence between these guys, okay, then you will see that this will give you a thermal state. So even though this is a Bell state with positive and negative, these are Bell states, two of them, then they will create thermometer state. If there is also environment here, and compare it with the mixture of two atoms instead of superposition, you can create a mixture also. If you compare it, there is a hierarchy of the temperatures. So symmetric Bell state is giving more temperature in the thermometer, showing more temperature on the thermometer relative to mixture and relative to the antisymmetric one. Then, can I go further to make Google happy? Yes, so let's increase the number of qubits. So far, with just only one coherence, your little demon has two arms to sort things out. Okay? But if you create more and more bigger decay-like states with more coherences here, you are giving more arms to the demon, and then it will become more efficient. Okay? Then we found that W-type states, or symmetric decay-like states, are very efficient in creating temperatures, and there's a trend like this. So this is the kind of dance matrix I am plotting here in the energy basis. Okay? So this is anti-diagonal and diagonal. Along the main diagonal, these are populations. Okay? And if you populate coherences around the main diagonal in these blocks, okay, these are thermal classical-like states that you can get, and you are just expanding, enhancing, augmenting the standard Carnot bound. You are not breaking it, but you are augmenting it. If you populate other coherences, like these guys, the green ones, okay, then you are injecting some coherence into the thermometer. Actually, it's in the form of displacement state, global displacement state. So it is like work-like. Okay? Then if you want to squeeze the information and create squeezing-like effects, then you have to go to this blue and the blue coherence. Green coherences are squeezing, and the blue ones are displacement. These are displacement, and these are squeezing coherences. Okay? So there is a map, and this always grows like this. Okay? So we also say there is an information molecule, so the vertical coherences that you can create in the ensemble in the atom, and horizontal coherences, they are heat-like and work-like naturally. Okay? So the trend is you can do some Young tableaus analysis of using the addition of multiple qubits spins 1/2. Okay? Then you can use group theoretical understanding of the sizes of these blocks. They follow a Pascal triangle, and then you can have a general result for n qubit cluster. And it always, the nice thing here is that you can never mix the heat-like quantity with a work-like quantity. They are disjoint completely. Okay? So we have some applications of that. one thing I want to mention is that when you go to larger and larger atomic clusters, you expose your system more to the environment and you suffer more to dephasing and decoherence. So the decoherence can also go with n square, okay, or n. So this time there is a supremacy of the thermal information states that they promise a quadratic enhancement in speed, also in processing power and memory as well. They all also here, but the problem is if the dephasing also scales up, then you cannot escape a macroeconomical law known as law of diminishing returns. Beyond a certain critical size, you have to lose benefits. Okay? And we verified that this also happens in our quantum information states of large clusters. So after a certain critical number of size, the quantum supremacy will go down. Okay? So we have some applications of that. Like we can use analogy of the information and the heat to propose unidirectional information transfer devices, also their thermal analogs known as quantum thermal diodes, information engines, also their thermal analogs with optomechanical systems that can be implemented using Frank Honorius' beautiful idea of circuit QED, and we'll make some resonators for operating like generating waste heat to electricity converters and so on. Okay? So these are my conclusions. So basically, classical thermodynamics can still bound the quantum machine with some augmented, maybe bound to laws, Carnot laws, but you can also break them using states without any temperature analog. Then you can have some applications of this in quantum heat engines to quantum simulators or phononic quantum computation to also use the temperature to create a quantum memory to protect long-lived quantum information states. Okay? So we are also doing some topological extension of this. There is a poster there. If it is still there, you can discuss with Elif. Then thank you. I hope I didn't break anything more in this talk. Thank you very much for your attention.
Thank you very much. Any questions?
What's the role of the Kelvin except for being a thermometer?
No, you can put here to other atoms as well. So it's just a quantum thermometer state. You can probe and measure it as, let's say, Stokes parameters of polarization, atomic Stokes parameters, populations, coherences, something that you can probe.
Thermodynamics does not have any role in thermodynamics.
Well, no, you derive the steady state of the master equation, of course. Yeah.
Any more questions?
I wouldn't pretend I understood a lot, but there was work of Mark Raisin.
Yes, negative temperatures and the breaking of second law, yes.
Right. So maybe if you're familiar, can you draw some?
Yeah. Of course, this work doesn't focus on the quantum coherence. It's a very old seminal paper. And the negative temperatures can also be a way to go beyond second law bounds, because in equilibrium systems, they are not considered in standard thermodynamical laws. So you can use this as a vector. But the problem with negative temperatures, they are highly unstable. So if you create them, they will easily, and also to create them in a large ensemble is very difficult. So this quantum information states, actually, with negative mass states, you can simulate these effects easily. With something that they cannot do, like in a practical sense, a negative temperature band, difficult to construct. But using quantum coherences with less inversion, you can get much larger negative temperatures. Yeah. So I didn't consider much this regime, but there are a lot of practical opportunities using quantum coherence. I just focused on this regime. But here you can get negative temperature with less population inversion using quantum coherence. So in this regime, you can escape a second law, like Mike Raisin suggested. But you can do it more practically using quantum coherent version, like negative mass version.
So let's thank the speaker again.
Thank you.